So my name is Dr. Patrick Alken, and I work in the geomagnetism group at the National Geophysical Data Center at NOAA. And one of the main tasks of our group is to produce models of the Earth's magnetic field. So the Earth's magnetic field is a big energy field. It's produced by many different sources. The primary source is molten iron, which is flowing around inside the Earth's core. And this creates electrical currents, which then create this big magnetic field which encompasses the planet. We created this data set, which is a magnetic declination data set, to kind of visualize how the magnetic field looks on different parts of the Earth and how you might use that for navigational purposes. At every point on the surface of the Earth, a magnetic field has a well-defined direction. However, if you have a magnetic compass, the compass needle will align itself in the direction of the magnetic field. But typically, that direction is not exactly pointing towards true north. So that angular difference between true north and the magnetic field is what we call magnetic declination. So the red and the blue just indicate the different conventions. So if you're standing in an area where the blue lines, we define that as negative declination, which simply means that if you have your compass needle would then be pointing toward the west of true north. And if you happen to be standing in one of the red regions, your compass needle would point eastward of the true north direction. And so we define eastward as positive declination and westward as negative. And so that's all that the color scheme represents. And if you happen to be standing on the green line, then your compass needle would actually point exactly in the direction of true north. So you get a zero declination in that location. And the time span of this goes all the way back to the year 1590, and it extends all the way up until the present day. And so back in 1590, primarily the people that were interested in magnetic declination were ships that were trying to navigate the oceans. So these ships would actually carry magnetic compasses with them and make measurements, and then they would need to correct that measurement with the local declination in order to understand what direction is true north so that they could navigate. In this animation, it shows you over several centuries how this declination is changing, but we don't really have a good understanding of why the magnetic field is changing, and it's very difficult to predict, even just a few years in the future, how what the field will look like. So for example, the green dot that's shown in the field of view right now is the magnetic north pole, and that is simply defined as the point where the magnetic field lines are vertical. And you can see that it's moving. For some periods of time it's very stable and it doesn't move that much. Other periods of time it moves faster. It's interesting because right now you can see that starting around the year 2000 it actually starts accelerating quite rapidly. So we don't understand exactly why this is happening. There are some scientists who suggest that we're in the early stages of a pole reversal. This is where the magnetic north and the south pole actually switch. And the last reversal was actually 750,000 years ago. And so you can argue that in kind of an average sense that we're overdue for a reversal. But of course we don't know for sure because we can't predict more than a few years ahead of time what the field is going to do. And so we need to kind of wait and see and improve our observations.